Welcome to the core curriculum on Explainable Artificial Intelligence, often abbreviated as XAI. In this foundational module, we will explore why interpretability is no longer optional, but an absolute necessity in modern machine learning. As data science advanced, we transitioned from highly visible linear equations to incredibly intricate architectures. We now deal with deep neural networks or massive gradient-boosted ensembles that function entirely as a black box. These structures ingest features and return remarkably accurate outputs, yet hide their underlying causal mechanics. In high-stakes environments like healthcare diagnostics, criminal justice, or automated financing, a lack of transparency translates directly to an inability to safely trust the system's decisions. Historically, practitioners found themselves restricted by a strict, inverse relationship known as the accuracy versus interpretability trade-off. On one extreme, algorithms like linear regression or shallow decision trees offer high transparency, but struggle to map intricate nonlinear dynamics, capping their accuracy. On the opposing extreme, deep architectures achieve unmatched performance by learning highly complex mathematical manifolds, but they do so by sacrificing human interpretability entirely. This conflict is precisely what Explainable AI seeks to resolve. When trying to break open a black box model, techniques generally fall into one of two major categories based on their target scope: global explanations and local explanations. Global mechanisms attempt to outline the macro behavior of the complete system. They help engineers map entire feature dependencies across an entire population dataset. In contrast, local explanations don't care about the total model architecture. They focus exclusively on a single instance to justify one particular decision. This micro-focus forms the foundation for LIME, the algorithm we will be studying next. Now we reach the heart of the lecture, the core idea behind LIME. LIME stands for Local, Interpretable, Model Agnostic Explanations. The term model agnostic means that LIME doesn't care about the internal architecture of your classifier. Whether it's a deep neural network or a random forest, LIME treats it as a black box that just takes inputs and returns probabilities. Imagine this plot represents the feature space of a complex model. The red wavy line is the decision boundary. Globally, this model is nonlinear and incredibly complex to explain. Now, suppose we want to explain one specific prediction. This white dot. This is where LIME becomes local. To explain this point, LIME generates a new dataset of perturbed samples. It takes our original point and tweaks its values slightly to create synthetic neighbors. LIME then observes how the complex model predicts these neighbors. Finally, it fits a simple, interpretable model, like this yellow linear regression line, to these samples. By fitting a line locally, we can easily see which features moved the needle. Locally, the complex curve looks like a simple line, giving us the intuition we need to trust the prediction. The first structural pillar is local approximation. Attempting to explain a highly complex model globally is a losing battle because the global decision boundary weaves through multidimensional space in a nonlinear fashion. However, look at what happens when we isolate a single observation and construct a hypersphere around it. Within this highly restricted local neighborhood, the complex global curve transforms into a simple geometric subspace that can be modeled effectively by a straight line. The second major concept is perturbation. LIME does not introspect the model weights. Instead, it probes the black box by generating a synthetic cohort. It accomplishes this by copying the original instance and applying slight random noise. For tabular data, this means altering numerical metrics or shifting categorical classifications. For image data, it implies hiding random segments of pixels. This step yields a dynamically generated data matrix flanking our true point. Third, we look at similarity weighting. Not all synthetic points are treated equally. Points generated near the original sample must have a stronger voice than variations created far away. Lime utilizes an exponential distance kernel to scale these weights. If a sample is mathematically distant, its influence drops off exponentially, enforcing strict local focus during optimization. Finally, we hit these weighted synthetic variations with an interpretable surrogate model, which is typically a regularized sparse linear regression model. Once fitted, the model parameters, specifically the coefficients or weights, translate directly into feature importance scores. A large positive coefficient implies that increasing that feature strongly drives the prediction forward. This gives us our final answer. In structured tabular data datasets, features contain real-world numbers or categorical tags. To perturb these features correctly, Lime reads the global dataset statistics to understand the mean and variance of every column. It then generates synthetic variations by drawing samples from a normal distribution centered on the instance data, ensuring the generated points accurately reflect valid baseline feature ranges. For natural language processing, text models ingest high-dimensional word embeddings. Lime abstracts this complexity entirely by mapping words into a basic binary vector space. Lime then creates perturbations by randomly changing ones to zeros in this vector. In the actual text document, this acts as a masking filter that completely drops those specific words out of the sentence structure. By tracking how the black box model shifts its sentiment probability score when words like horrible or trash disappear, Lime isolates the exact text triggers driving the prediction. Finally, we observe image classification. Standard deep networks read single pixels, but running single pixel alterations would completely destroy localized contextual structure and mean nothing to the model. To solve this, Image Lime bundles pixels into patch groupings called superpixels using localized segmentation algorithms. It then generates synthetic iterations by graying out random segments. If masking out a specific superpixel causes the classification probability score to drop from 90% down to 0, that hidden segment is marked as highly critical to the final output. While Lime is powerful, it has critical engineering flaws. The first is instability. Because Lime relies on random perturbations to build its local dataset, it is fundamentally stochastic. If you execute Lime twice on the exact same data point, you might get noticeably different feature importance rankings. This lack of deterministic consistency makes it incredibly difficult to deploy in strict regulatory environments. The second major drawback is the kernel width dilemma. Lime requires you to define a proximity kernel parameter that controls the size of the local neighborhood. If your kernel radius is too small, your surrogate model overfits to unrepresentative local noise. If it is too large, the linear model attempts to optimize over nonlinear spaces, completely violating the core premise of a local approximation. Finally, researchers discovered that Lime is highly vulnerable to adversarial manipulation, often called scaffolding attacks. A malicious actor can wrap a highly biased model inside an adversarial check. Because synthetic data distributions look distinctly different from actual user metrics, the model quickly detects if Lime is auditing it. When it detects an audit, it dynamically hides its bias and outputs completely fair predictions. When a real customer submits data, it resumes its biased behavior undetected. This flaw proves that post hoc explainers cannot fix an inherently corrupt model. Welcome to this lecture series on SHAP, which stands for Shapley Additive Explanations. In this first section, we will uncover the core philosophy behind SHAP and explore how it adapts principles from economic game theory to make complex machine learning models transparent. Modern machine learning algorithms like XGBoost, random forests, or deep neural networks are incredibly powerful. However, they operate as black boxes. We feed in features, and we get a highly accurate prediction out, but we lose the ability to see exactly how individual variables drove that outcome. This lack of transparency introduces severe risks regarding bias, regulatory compliance, and simple human trust. This is the exact engineering problem that SHAP solves. Instead of trying to explain how the entire model works globally all at once, SHAP answers a highly localized, precise question. How much did each feature alter this specific prediction relative to the expected baseline average prediction across the whole dataset? To accomplish this, SHAP abstracts machine learning variables into a concept from cooperative game theory. Imagine a business coalition or a competitive tournament where multiple individuals work as a team. In this framing, each variable or feature in your dataset acts as a single player in a game. The unique combination of these features generates an outcome. This final model prediction is viewed as the total financial payout or reward achieved by the coalition's joint effort. Now, here lies the classical game theory dilemma. If the team makes a great profit, how do you fairly distribute that total payout among the members? Some features are highly influential, while others may only be powerful when paired synergistically with someone else. SHAP resolves this distribution problem utilizing Shapley values, an axiomatic attribution mechanism invented by Nobel laureate Lloyd Shapley in 1953. This mathematical framework guarantees a completely fair allocation by calculating the exact marginal contribution of each player across every single possible sub-coalition of features. We will dive into the core technical engine of SHAP. We will explore how baseline models establish a starting point, how feature combinations are weighted, and why the additivity property makes SHAP uniquely powerful. Every SHAP explanation begins at the base value, denoted mathematically as the expected value of f of x. This represents the average prediction of the model across the entire training dataset. Think of it as the model's blind guess before seeing any specific features. When we introduce specific features for a single instance, they act like forces pulling the prediction away from the baseline. For example, a high-income feature might act as a positive force, adding 25 points to our score. Conversely, a poor credit history acts as a negative force, dragging the prediction down by 15 points. These individual shifts, positive or negative, are the exact SHAP values for these specific features. The summation of these positive and negative forces lands us perfectly on our final model. Prediction output. which in this case is 60. To find these exact numbers fairly, SHAP evaluates features across all possible combinations or subsets. But not all subsets are treated equally. The game theory weight profile relies heavily on coalition size. The combinations get a U-shaped weight pattern. Tiny subsets containing an isolated feature receive massive weight to capture pure main effects. Grand coalitions containing nearly all features also receive massive weight to see total. Interaction behavior. Middle-sized coalitions get lower relative weights. This brings us to the bedrock mathematical rule of SHAP, the additivity property. It guarantees that for any local explanation, the final model prediction f of x is precisely equal to the baseline expected value phi 0 plus the linear sum of all individual feature SHAP values. Phi I. Why is this property so important? Many other explanation methods drop complex interactions or approximate loosely, leaving gaps. SHAP's additivity guarantees perfect conservation of attribution. 100% of the variance between the average benchmark and the real prediction is perfectly accounted for without any mathematical leakage. This is the classical Shapley value equation. While it looks intimidating at first glance, it breaks down into two distinct, highly logical operations: computing a raw marginal contribution for a subset, and multiplying it by a strict combinatorial penalty weight based on permutation mechanics. To find the marginal contribution of a specific target feature, let's call it credit score, we first evaluate our model's output using a base subcoalition. Here, a coalition containing only age and income predicts a value of $300,000. Next, we join our target feature, credit score, to that exact subcoalition. With credit score included, the model prediction shifts to $380,000. The raw difference between these two predictions, $80,000, is the isolated marginal contribution of credit score to this specific group of features. But this is only one potential combination. To be truly fair, we must test all combinations. Let's build out the data. First, if feature A joins an empty room, the model output moves from a baseline of 10 up to 50. The marginal contribution here is 40. Next, what if feature B is already present? When A joins the alliance of B, prediction shifts from 20 to 70. This yields a marginal contribution of 50. We repeat this process across all remaining combinations. We look at the subset containing only C, and finally the subset containing both B and C. Now we apply the permutation weights. In a 3-player game, subsets of size 0 and size 2 receive a weight of 1/3. Subsets of size 1 receive a weight of 1/6. We multiply each marginal score by its corresponding structural weight. Summing up these intermediate configurations gives 13.33, plus 8.33, plus 6.67, plus 15. This yields a final Shapley value of 43.33. This is the precise, mathematically unbiased contribution of feature A for this distinct local data row. For a model with 3 features, labeled A, B, and C, the math maps out the full power set of coalitions. We start at the top layer with an empty set containing 0 active features. We then generate the single element layers, evaluating features completely isolated from each other. Next come the pairs, and finally the grand coalition containing all 3 elements. This produces 2 to the n, or exactly 8 distinct feature combinations that our machine learning model must evaluate. To find the definitive SHAP value for feature A, we track every transition edge where feature A is added to a subset. We calculate its marginal contribution at every single layer shown by these paths. Now, let's derive the exact mathematical proof for the weighting factor. Think of building a model feature by feature as an ordered arrival sequence. For a total feature set N, there are exactly n factorial total unique sequence permutations to order their entry. If feature I joins a pre-existing subcoalition subset s, those features inside s must have arrived before I. The number of unique ways to arrange those initial members is the size of s factorial. Similarly, all remaining features must arrive after feature I. The count of these remaining features is the total size N minus the size of s minus 1 for feature I itself. They can be arranged in N minus s minus 1 factorial ways. Multiplying these two localized ordering choices together gives us the total number of permutations, where feature I joins subset S. Dividing this value by the absolute total pool of n factorial sequences yields the exact probability weight applied in our master equation. Let's view a second concrete case of feature sequence mechanics. Consider a machine learning model predicting real estate prices. Features rarely add value independently. For instance, adding an extra bedroom means very little if the overall square footage is constrained. Our core real estate inputs are square footage, bedrooms, walkability score, and year built. To understand how entry order shifts localized valuation weights, let's step through two different sequential combinations. In sequence 1, square footage is added first to the baseline asset profile. The model valuation leaps up by $150,000. Next, the number of bedrooms joins the mix. Because we already established that the house has significant square footage, adding more rooms is highly viable, increasing price by $60,000. Walkability score enters third, tacking on $30,000 to the valuation. Finally, year built arrives. Because this specific property is older than the market average, the model drops the appraisal value down to $520,000. Now let's flip the priority order. What happens if bedrooms arrives first, before we even establish the size of the house? Adding bedrooms to an unknown footprint only provides a minor $15,000 bump. But when square footage is added second, it justifies the existing rooms and validates the space. The valuation shoots up by $195,000. The remaining features join, bringing the final asset back down to the identical grand coalition outcome. Two sequences are easy to look at, but what about the remaining 22 paths? The SHAP engine must rapidly loop through every single ordering permutation to extract an unbiased, mathematically sound valuation map. By calculating the exact mathematical average of marginal contributions across all 24 distinct permutations, the variance is fully resolved. The extreme interaction swings cancel out, leaving us with a clean, unbiased attribution for each feature. The final attributions sum up exactly to positive $220,000, moving perfectly from our $300,000 baseline to the $520,000 $1,000 target. Before we can compute local feature impacts or stack them into global population maps, we must establish the starting line. In cooperative game theory, a game begins at 0, but a machine learning model cannot run on an empty feature set. Let us look at how SHAP defines the zero-feature baseline reference state. To simulate a scenario where 0 features are known, SHAP computes the expected value of the model over a background reference distribution. This is done by passing a representative slice of the training data through the model and averaging all predictions. In this credit risk lecture scenario, averaging out the background population yields a definitive base value of 15%. This represents the global unconditioned risk expectation. Every local SHAP attribution explains a variance away from this exact baseline benchmark. Let's view the local scale with a specific applicant, John Doe. The model predicts his default risk is 42%. A local explanation answers, how did we shift from our baseline expected value of 15% up to this final 42% decision? The local SHAP explanation breaks this variance down. Starting from 15%, his low credit score pushes risk up by 18%. His high debt ratio adds another 12%. Meanwhile, his strong income pulls his risk profile back down by 3%. These local allocations match the model delta exactly. To find a global overview across the business, SHAP doesn't run a separate metric. It simply stacks thousands of these local deviations from the baseline expected value together. Every dot on this summary graph matches a single local prediction variance. Red signals high feature parameters, while blue denotes a low metric layer. By evaluating the horizontal displacement from 0, we uncover global insights directly structured from consistent, underlying local truths. Thus, our global feature spectrum is the mean absolute value of our local variations. From the background distribution expectation to micro-audits and global population overview maps, SHAP unifies machine learning interpretability.